Okay, this is our Chapter 9 lecture. And Chapter 9 is going to be on, let's move the screen down a little bit, water resources, global water resources and global water use. It's more of an introductory chapter into, there certain things that water is used for outside of what we normally think of when we think about water use. A little bit more detail on some of the uses of water. And it's more just kind of setting us up for when we talk about water pollution and having a better understanding of what happens in with pollutants that can get into the water and cause some ecological damage there. So the case study for the book is about the river in Oregon, the Klamath River, 250 miles of river. Was at the time, pre-development, considered the third largest salmon fishery on the West Coast. Basically, it was the third largest place where salmon fishermen could get, for the commercial industry, could fish out salmon to be sold. But it's undergone some development changes. It's been dammed in different areas to generate electricity. So when we talk about hydroelectric power and renewable energy resources, we'll get into more of the specifics of that. But damming the river up does change the water's flow, and it does flood certain areas where the damming is occurring. Water's been diverted for irrigation and farming in the area around the river. And all of this has led to salmon populations getting reduced, which has affected there's a lot of local Native American tribes in the area that have relied on the salmon as a source of food, and the fishing industry as well that has relied on as a source of income. So we normally think about water use as, physically us using water, but we don't really think about the things that are considered resources that are reliant on water as well, like fish and other wildlife, and the effects that it can have on that. So with something like a river, which isn't owned by anybody, there's been a lot of conflicts between the interest groups. So we're talking about the local tribesmen, we're talking about the fishing industry, the electric companies, about who is allowed to use that river for certain things, because one group's interest has negative impacts on the other. So when we focus on global water resources, we see that the idea of ownership is very controversial when it comes to water resources specifically. Now when we talk about usable water, so now we're talking about fresh water here specifically, as can be used by humans, because again, environmental science does talk about the human impact. So you should know that only about 3% of all water on the earth is considered fresh water. Now, if we break down that 3% of water into another table, we see that about 75% of that, a little bit more, is found in ice and glaciers, so it's basically locked away, unusable. Small pieces are 0.03% is atmospheric water vapor in the air. About 0.5% is considered water bodies. So now we're talking about, these are all of your freshwater biomes, your lakes, your wetlands, things of that nature, streams, rivers. So when you think about how much water that is on a global scale and how it only makes up 0.5%, so what we don't realize is that a good chunk of our usable freshwater comes from below ground, from these underwater aquifers. And an aquifer is basically just a confined space underground that is holding water. The water can enter it by percolating through it. Basically, we talked about permeability and porosity in Chapter 8, and that water can maneuver its way through the ground. And as it does that, it gets cleaned of things like bacteria and other particulate matter, and can basically stay nice and, confined and just hang out in this little space underground. There are two types of aquifers. There's unconfined and there's confined. An unconfined aquifer is usually on top. That means that you've got porous rock covered by soil. This is something that might feed into like a river or a stream, and these are basically closer to the surface. Confined ones are separated by a layer of impermeable rock, which means that water is getting there from some other source. So if you take a look at this diagram, it gives you a pretty good idea of the difference. So here we see that the unconfined aquifer here is the bottom of which is part of a little pond river here that's running through it, and you see that it's basically laying right below the soil here. There's this layer of impermeable rock that this water cannot get through, which separates it from this other space. that creates this confined aquifer, which is probably being charged from maybe like some melting snow or a glacier somewhere. I shouldn't say glacier, I should say melting snow or retreating glaciers, not melting glaciers. So when we talk about groundwater in these aquifers, so the level that the aquifer contains water at is considered the water table. So when you hear water table, we're basically talking about how high up does the saturated soil go. Basically, if we were to go into this area, we could pull out water from, to the point where that soil is pretty much fully saturated. It can't hold any more water. If it holds any more water, it's going to start flooding to an extent. The idea of recharge, so you saw in this slide that recharge area here. Recharge is basically inputting, so melting snow, rainwater collection, retreating glaciers as they are melting. It does, the idea is that as a glacier melts, ice goes from being ice to liquid water. It doesn't take up as much space, doesn't cover as much surface area. So that as that happens, we say the glaciers retreat back to their basically central location. And a spring. So a spring is basically where water from an aquifer might naturally make its way to the surface. Now, springs are, if you want to think of an easy way to remember what a spring is, think Poland Spring and other bottled water companies that get their water from springs. What they're basically getting their water from is a location where these underground aquifers reach the surface at some point, on somewhere on a mountain or a sloping hill, and can that water actually, like the picture is demonstrating here, actually feeds out into a local, basically turns into a river or some kind of stream. Now with groundwater, one of the concerns we have is that getting water out of the ground does lower the water table. It's physical conservation of matter. We're taking water out of this soil. So the area that water gets taken out, it's kind of like a drain. The drain in a sink, if it's filled with water, is going to be the first place that the water dips down to, and you might see that swirly little cone happening there, because that's where all the water is getting taken out. Well, the same idea happens with the water table. When wells are overused, they create these cones of depression, and where they're relevant is that, you can see in the example here, this individual's well on this farm here extends much deeper, probably because he needs to ensure that he gets a lot of water to irrigate his crops, whereas these homes that have their own wells don't dig nearly as deep. Well, this farm is using up a bunch of water for irrigation. It might lower the water table to the point where it could dry out the wells of these individuals, and then they're going to have to spend money and have to get their water resources elsewhere, maybe digging new wells, and that could all be expensive. Another issue with groundwater, overuse of groundwater, is saltwater intrusion. And obviously, since we're talking about saltwater and talking about the oceans, this is a problem for coastal areas only. But the same idea. Rather than a well creating a cone of depression that deprives other wells of water, what this does is lower the water table to the point where below sea level, which might actually allow, because we are trying to pull in water, so the water is going to move to fill that space, could actually add salt water into that water table, and which would basically mean that these people are pumping salt water into their wells, and salt water is not good for people to drink, not good for crops. So that's an issue facing coastal areas that overuse their groundwater and overuse their aquifers. So that's groundwater and aquifers, which are pretty much our major source of getting water. Now, other sources of fresh water are surface water, streams, rivers, ponds, lakes, and wetlands. So if you take a look at these couple of graphs here, in terms of volume, maximum depth in meters, and surface area, how much they cover, you can see that these big bodies of water that we're used to thinking about aren't so big in comparison to each other. Now, when we also talk about surface water, we're talking about primary productivity, because we know that lakes are breeding grounds for things like algae. So another concern of surface water is how much activity is happening in that lake. If you might remember eutrophic zones from talking about phosphorus cycle. So an area that's considered eutrophic has high levels of primary productivity. High algae growth usually is a good sign of nutrient availability in that area. So when you have a lot of extra nutrients available, like runoff of phosphorus and nitrogen from waste, you have this high productivity that leads to dead zones because of a lack of oxygen. It's just some of the terminology that goes along with productivity levels in freshwater things like lakes. Oligotrophic means you have a low amount of nutrients, so you're going to have low productivity. Mesotrophic, a medium, mid-range amount of nutrients, and therefore a moderate level of productivity. And of course, eutrophic, meaning high levels of productivity and because of high levels of nutrients. All right, so how do we alter the availability of water? Basically, what can we do to change where water goes physically, manually? Smaller things that are used are levees and dikes. Now, the difference being that levees are used to basically keep a river from flooding into a particular area. So you see in this picture here, this area here, where this white sandbags are, is in that brown road-looking area. That was a levee that was separating this, which was farmland, from this river here. Levee broke, and this water was allowed to spill into this area and cause it to flood, hence the mixing of dirt and stuff. And you can see that this is clear blue water, and this is very murky, muddy water because of all this ground and soil that was there. So levees are basically built up to separate rivers from other areas. Dikes are more used in areas that are below sea level, which is why they're very popular in Northern European countries. They basically protect the grounded land, farmlands and other areas where people live, suburban and urban areas, that are physically below sea level from from the actual ocean and seawater that is technically above them in terms of height. They're very similar, except they're basically just focusing on ocean waters, whereas levees are more smaller, designed to prevent things like rivers from overflowing. On a larger scale, dams are basically not just used to separate rivers from certain areas, but physically to separate rivers from themselves. They can run across rivers and streams. They control the flow of water, usually to flood a particular area in order to do some landscaping or development. Dams are good for that, and more commonly, with a lot of newer dams being built, is the idea of hydroelectric power, using that flowing water through that dam to generate electricity. The area where the water is stored behind a dam is basically considered a reservoir. That's the term. That's what that means. Is that's pretty much the area that we're going to find all of that water that's backed up as it's approaching the dam to flow through it. And reservoirs are areas where we can get fresh water from. So things like any kind of reservoir, especially in this area. Reservoirs are where a lot of rainwater gets collected, and when the rainwater is collected, it's then pumped off to water companies that then distribute it to individual households. Now, the problem with dams is that because they are so intrusive, they do affect the movement of animals, and they basically can have a big impact on migrating organisms like salmon. So one thing that has been more of an environmental invention that's helped with this problem has been the idea of fish ladders, and their benefits are that they allow fish to basically move across an area where a dam is built or a river has been dammed up, where the dam is still doing its job of whatever it's supposed to do, whether it's blocking an area up, allowing water to flow through it for electricity, but the actual fish itself can still move from one side to the other relatively safely by basically jumping or moving through these system of ladders in little pools. Now, aqueducts are another method of moving water as well from one location to another. These are very old school. They're still used today. They're basically large canals or ditches that basically drag water from a larger location to another. They're not as common anymore because we have a lot of piping, but they were kind of the original water pipes for transporting water from one large area to another. And a newer concept in terms of water availability, because we looked at how much salt water there is compared to fresh water, is the idea of desalinating water, basically taking the salt out of it in order to obtain fresh water, which can then be used by people as well. There's two main methods of water desalination: distillation and reverse osmosis. So to sum the two up, distillation is basically boiling water to get steam and then collecting the condensed fresh water in that chamber. So the water gets heated up here, and then it hits very cold coils that the water itself is flowing through. And when it hits that, it condenses from steam back to a liquid, and this side collects the fresh water, and the what we call brine, which is very, very salty water, is flown out into that chamber and more or less back into the ocean to recirculate. The other idea is reverse osmosis. So if you remember osmosis from biology, high to low concentrations, basically pressure here forces the water through this semi-permeable membrane that the water can get through, and resulting in fresh water, that the salt and briny water stays on this side and flows out. Since the salt water is going to be denser, it basically flows out here, and more salt water can flow in to then be desalinated. So what does all of this, why do we focus on freshwater availability? Mostly because we need and use, not just for individual survival, because we know living things need water, but from the human side of it, as a culture, we use water for a number of different things. Agriculture is the largest user of water around the world. These are 4 of the main types of irrigation: furrow, flood, spray, and drip. The next slide has definitions and explanations of all of them, but the idea is that furrow is considered the least efficient of all of them, where it's basically these ditches and canals that the water flows into, and then the water is then soaked up by the soil. About 60 to 70% efficient. Flood is about 75%. Spray 75 to 80. Drip is being the most efficient in terms of water use, and in terms of how much is lost to evaporation, about 95% for your traditional farming techniques. Now, there's also hydroponic agriculture. So these are our 4 basic, summaries of those different kinds. And as you're reading this, if you want to flip back and forth between to get an idea of, okay, that's what they mean when they're talking about this, you can see where each one has their own benefits. And obviously, the most efficient use is what we would like to focus on, which is why hydroponic agriculture has become so popular, because what it basically involves is using fertilized water and no soil at all, meaning that these crops can be grown indoors in basically these trenches, and then the fertilized water doesn't have to be, doesn't get lost into the soil. It can be recycled and reused. You don't lose any to evaporation, and it's basically cut water use compared to traditional agricultural methods, these one here, by like 90%. Can be expensive, but it is right now mostly small scale, but it is promising that this method of irrigation and crop growing is becoming more and more prominent in terms of its ability to save water. Industry is the second largest user of water worldwide. Things like energy generation, so cooling. So here we see a power plant and the cooling towers for water. Water is very important in energy generation. Every type of electricity generated requires water in some way, shape, or form, with the exception of solar and wind. Good production, finishing processes of producing goods. Basically about a little less than half of all water that is used for industry. The bulk of which is used for agriculture. Industry falls in second, and then household needs is last. Household needs are things like bathing, cleaning, showering, cooking, things like that. And you see toilet flushing, bathing, laundry, which is why there's been an emphasis on low-flow toilets and showers and washing machines, because that is where the most water use in the household is coming from. And being able to limit the amount of water used here can definitely save on the amount of water used in the United States, which you can tell from this graph is our 3rd largest user of water per capita. Last slide here is talking about future, and this is going to be an interesting topic, as water, which is a common resource, doesn't really have any kind of ownership. We have the rights to use water, so going back to that original case study involving the river in Oregon, nobody owns that river, but people have the rights to use that river and to use the water and basically the things that are in it. So it's going to be interesting to see if water ownership becomes if water becomes a commodity, and there are some countries that are experimenting with this. I believe Chile being one of them, that is pricing water as a commodity, basically a buyable and tradable item. The ability to own water is going to be very interesting in the future because of its necessity to life, and if it does become a scarce resource and a limiting resource at some point. For our human population, the ability to claim ownership over a water resource and therefore to profit off of it is going to be a very big question mark going forward. And of course, water conservation. So we'll focus a little bit more on specifically some of the things that are done to conserve water. Hydroponic agriculture is an example of that. More efficient in terms of household use, things like water fixtures, low-flow toilets, and showers, washing machines that use less water, hoses and sprinklers that use less water to water household and personal lawns, car washes that use water more efficiently and recycle water and things of that nature. And that's basically it for the water resources. So you should know some of the technical terms for aquifers and where this groundwater and where this fresh water, I should say, is located. Not just groundwater, but surface water as well. And then for use, you should know the different kinds of irrigation that are related to agriculture. Examples of industrial, which we'll talk about more when we do energy a little bit, and obviously household uses, which we're all pretty familiar with. And that basically sums up everything in Chapter 9 for our water resources, which we'll spend about a week on and then move on to to land management and land use, which will be a slightly larger topic the week after that. So enjoy your weekend and see you all next time in class.